Hello everyone, welcome to our first video on the topic of differential equations. As you can tell, I got my headset mic on. I look like I'm about to ask you if you want to value size your meal at the drive-through window, but it's okay, no one's here to see me, so I can keep my shame in private inside my classroom. Alright, but anyway, I want this to be a fairly quick video, quicker than the last one, so let's get right into it. So basically a differential equation is just any equation for the derivative of a particular function, which includes an initial condition. And we've actually looked at a couple differential equations already when we were solving antiderivatives. Y'all remember this? This is the differential equation right here. It basically says when my function x is a certain value, my function y is going to be that other value. Remember, we need an initial condition because of that constant c that comes out of the integration. Okay, and so there are two types of solutions we can get to differential equations. One of them is the general solution, in which case we just leave that c right where it is. We don't worry about solving that. So in a general solution, sometimes you're not given an initial condition, or sometimes you're given an initial condition and you're just asked to solve the general solution. You don't actually have to apply it. Then we have a particular solution. Sometimes this is also called the exact solution. And in the exact solution, we apply our initial condition and we solve for that variable c. Now, some of you guys might be looking at this equation right up here and saying, wait a second, why do I have a function of x and y in here? Well, don't worry about it. I'll get to that, okay? But basically, this first equation just says our derivative dy dx is going to be some function of the variable x and our solution y, okay? But it doesn't have to be. It could be just a function of y. It could be just a function of x. It doesn't matter. So the method that we use to solve these is something called separation of variables, and it's a very simple method to understand. Depending on what function you're doing it on, it can be hard or fairly easy to apply. But basically, you move everything with an x or everything related to x over on one side of the equation and everything related to y over on the other side of the equation. So if we do this, you'll see why this becomes an effective method to solve for our solution. So again, the solution that we want to find in this particular example, we want to find that function y. What is it going to be? Okay, so if we apply separation of variables and we move all the x things over to one side of the equation, well, what are our x things? We have a 5x and we have a dx. So if we multiply both sides by dx, we end up with something that looks like dy is equal to 5x dx. Now, some of you might be saying, oh, we can solve for y right now. How do we do it? We take the integral, the indefinite integral of both sides of the equation. Now the integral of 1 dy, or just the integral of dy, that's just going to give us the variable y. And then the integral of 5x, that'll be 5 halves x squared. And then we add our plus c. Now some people might be saying, why did we not add that plus c to the side with the y? Well, the reason is, yeah, we technically did add it, but then we'll subtract that c from both sides, and then whenever you add or subtract a constant from another constant, whenever you divide a constant by a constant, whenever you multiply a constant by a constant, you just get another constant. So we don't have to worry about that other constant we get from doing that left-hand side integration. We can all just collect it as saying, oh, that's just a constant c. Okay? So now that we got what this is, remember again, this is the general solution. Okay, we don't solve for that c. If we want the particular or the exact solution, we apply our initial condition. Our initial condition is that when x is 0, y is going to be 0. So we have 0 equals 5 halves 0 squared plus c. This means c is equal to 0, and therefore we get our exact solution, y is equal to 5 halves x squared. And we'll say that is the particular solution. All right, so just like we had before, we can always check to make sure that this equation is actually a solution to the differential equation. If we take the derivative of our particular solution right here, you'll notice we just get 5x again, okay? So it is a solution, it does work, it meets the initial condition, everything is awesome, all right? So let's look at one that's a little bit more involved, a little bit more complicated. Okay, so now we have this one. Now, why don't you yourself try to solve this particular problem? See if you can come up with a solution on your own. So pause the video. All right, so if you tried this one again, the variables separate very nicely in this one. If we multiply both sides by dx and multiply both sides by 2y, we'll end up with something that looks like this. 2y dy is equal to x squared dx, okay? And then we can integrate both sides of that, and we'll end up with y squared. Remember, we don't worry about the c on this left-hand side or on the y side, is equal to 1/3 x cubed plus c. And again, if we solve for this, we'll have the square root of 1/3 x cubed plus c. This is going to be, again, our general solution, the one where we don't solve for c. And then if we want to solve for c again, we just apply the same initial condition. Now, I gave us actually a pretty boring initial condition. Let's make, let's spice this one up a little bit. Let's make our initial condition, let's say y of 0 is 1. Let's just see what that does, okay? So I'm sorry if you already went through and solved this whole thing, but I just realized, I was like, that's kind of a lame initial condition. Let's try one that's a little bit more exciting, because that's what we're all about in the BC Calculus class. We like excitement, we like thrills. After class is over, we go base jumping. Okay, so anyway, if we apply this initial condition, now we'll get 1 is equal to the square root of 1/3 0 cubed plus c. And this tells us, I mean, it's not that exciting, but it just tells us that c is equal to 1. So therefore, our solution becomes y is the square root of 1/3 x cubed plus 1. And awesome, there we go. And remember, this is our particular solution. That word particular means like the exact solution. Okay, so again, let's look at now how we can take the derivative of that particular solution and end up getting the exact function we started with. All right, so let's go down here. If I choose to evaluate this derivative, okay, and again, we're starting with this equation right down here. Well, dy dx, we're going to have to use the chain rule for that. That's going to be 1/2 1/3 x cubed plus 1 to the negative 1/2 multiplied by the derivative of the inside, which will just end up being x squared. If we rearrange this, we're going to get x squared over 2 times the square root of 1/3 x cubed plus 1. And do you see it? Do you see it? What is 1 square root of 1/3 x cubed plus 1? That's just y. Okay, so our solution ends up being x squared over 2y, and let's see what the original derivative we were given was. X squared over 2y. So it works, okay? So that's the check. Same as with evaluating antiderivatives, you can always just take the derivative of your solution and see if it just gives you the differential equation again. That's always a check we can apply.